right, thank you. So I'll talk to you about some of our experience on building a lock-free B+tree on persistent memory. So of course, this is joint work with my student, Xiangpeng Hao. And so he's the reason that I can talk about this today. But before I actually talk about trees, I need to fill in you some of the background here. So a little bit like 3 years ago, we came up with this persist multi-word compare swap primitive, or PMwCAS, right? So this thing allows you to atomically change multiple 8-byte words atomically. And basically, you can specify following the CAS or the compare swap instruction interface, which is provided by the hardware to say, these are the words I want to change, these are the expected values, and these are the new values, and then boom, you can issue multiple such requests using this tool. So this one is software only and lock-free. We based it actually on a previous proposal done by Tim Harris and others in early 2000s. And we made it work on persistent memory. So basically, we used the PMDK to manage the persistent memory space, including things like pointers. We're using the persistent pointers so that we don't need to worry about these things. And also, we made it work so that we can recover from failures, persisted all the descriptors, which we'll see in the next slide, so that we can actually get the data structure back to a previous consistent state. So, and also, there's well thought out mechanism for interactions with persistent allocator, which again, we'll see later. So this one is now open sourced at Microsoft GitHub, and we're continuing to maintaining and improving it. So the overall goal here, you might wonder, why do we want this, right? So the idea is basically we want to simplify lock-free programming on persistent memory. So it's already really hard to do lock-free programming, and even harder on persistent memory, right? So that's why we want to do this. So a little bit more detail about how this primitive works is that basically it's based on the concept called descriptors. We follow the CAS interface for each word. Here, say we have this descriptor, and you have the address for the word you want to change, the expected value that you expect it to be here as a kind of successful condition, and then also the desired new value that you want to put on that word. So there could be multiple such words that's included in a single descriptor, and that pretty much describes the entire operation. And also here, notice that this is a fixed size thing, right? So it's pretty much we align it to cache line boundaries. And then 4 words maximum. That's the initial design. We'll come back to this later. And there's also some status information that you have to maintain to track the progress of the PMwCAS operation. So basically, after you fill in all these details, you can issue this PMwCAS operation. Say, I want to do it now. And then the final result would be either all the words are changed or none of them. Right? So they're all changed only if these expected values match what's actually there on the memory words. Okay, so that's basically the idea of this PMwCAS library. And now, again, before I talk about trees, I want to show you some simple examples. So here, I hope you can see this. Right? Basically, this is an implementation using just a single word CAS to build a lock-free double linked list. Right? So double linked list, if you think about it in single-threaded scenario, it's really simple. Right? So you just traverse to the right location, like we do similarly here, but this is lock-free code. And then you try to link the new node with the predecessor and also the successor, right? But what's different here is that in this lock-free code, you would have to first think about all the possible scenarios and see whether other people is also trying to do the same thing on the same location. And then finally, you can do this single word CAS, which only links you with the previous node, right? And then after that, if we succeeded, then that's fine. We can jump out of this loop and then come back to this last step where you actually link the successor node with this current new node, right? But if this thing failed, then you would have to come back to this loop again and retraverse and redo everything again, right? So this is only half of the story, right? So the next thing you do is actually using this same kind of more complex algorithm to just link the successor node with the new node here, right? Because you have to account the fact that there might be some other threads running at the same time doing exactly the same things on the same location, right? So you have to account all these facts, which is pretty much this part, and also you need a bunch of CAS instructions here, right? So this is what it looks like if you want to implement a simple double linked list with single word CAS, right? And by the way, this one by itself is a research paper, although it's back in the 90s. So this is what it looks like when you use multi-word compare swap. Pretty much here it's the same, right? You just traverse to the right location and prepare the new node. But what's much easier is this part. Basically, you say, I want to do a multi-word compare swap, and I want to link my new node with the previous, the predecessor, and also now I also want another entry in the descriptor saying I want to link the successor node with my new node, right? And then you issue that the PMwCAS operation. If it succeeds, then that's it, right? So pretty much all you need to do is to specify all this information here. And there's actually more things we need to do, but we'll save that for later when we talk about trees. So this is actually a much easier implementation. This is one of the kind of success story of PMwCAS we always talk about when we talk about this to the audience. So now you might wonder, of course, this is trivial, right? We want to build more complex data structure. And here we set out to build something called the BzTree. By the way, we didn't really propose this tree. It's just because we are trying to evaluate a bunch of trees that were proposed for persistent memory. Then we have to implement it, right? So this is a B+tree variant proposed by Microsoft Research, and they're using the PMwCAS operation to do this. So it's follows the B+tree design, where you have your data in the leaf nodes, and the internal node only guides the traffic to the right location. But it's also a little bit different and unique in the sense that you actually have the internal nodes being copy on write. So in other words, whenever you want to insert into an internal node, say as a part of the split or merge operation, for merge operation you would remove the keys, then you have to copy the entire node and then do the modifications and install it again, right? So the reason they do this is because they want it to be always sorted and also optimized for kind of binary search. But for leaf nodes here, they actually allow in-place updates. So the reason they want to do this is because we can quickly absorb more inserts in the leaf level, which is a thing that will happen often. But the internal nodes, they're modified relatively less frequently. So that's why they want to keep it sorted, but make it copy on write. Okay, and here by copy on write, what I really mean is copy on insert or delete. It only happens when you put a new key in it or remove a key from it. It doesn't have to be copy on write if you just update a pointer that's in that that's already in that internal node. Okay. So to note that this one was actually designed before the actual hardware came out, and in the paper actually what's kind of they targeted more on the NVDIMM devices, which makes it easy for them to actually measure performance without doing any emulation, because it's exactly the same DRAM performance there. So what we did here is a faithful implementation of this whole tree following the paper in order to evaluate as part of a collaboration with SAP and TU Dresden. So if you were here in this room yesterday, you probably have heard Lucas already talking about some of our results. So today I'll just skip all the performance numbers and just talk about implementation. Okay, so there are a lot of tiny details here, but the most important part is actually the structure modification operations, or SMOs. In other words, the tree split and merge operations. So I'll focus on tree split here. So this is how basically it works in the BzTree. It's a two-step process. So first of all, let's say we have this node here, which is a leaf node, and it's twofold, or the capacity, the size of the keys, the data there exceeding some threshold, then you need to split it into two. So the first step here we do is to sort of freeze this node so that no more inserts are allowed in this node anymore. So this is done by using a single word PMwCAS. So basically, they have some internal bits that says whether this node is open for new inserts. So basically, all you need to do is just toggle this frozen bit. So meaning it's not open for more inserts anymore. Okay. So that's one PMWCAS, simple and straightforward.
So
yes.
Quick question, just to make sure I understand why you need the CAS here. You need to know that you're the one who turned on the frozen bit.
Right. Yeah. Yeah. Okay. So essentially, this is the frozen bit is actually part of the another variable that also has other states. So you have to also make sure that something else doesn't happen as you flip this bit.
So if you're not the one who turned on the frozen bit, you'll end up going back around your loop again.
Well, yes. Well, but you also need to check whether someone else already flipped it before you retry it.
Okay.
Right. Yeah. So that variable actually also contains things like how much data you have in this node, the number of keys and space and so on. So you want to be kind of like atomically this operation happens in the kind of timeline, right? Yeah. So that's the first step, and then now we have frozen the node, so no one else can insert to it. Then the second step is called installation phase. Right? So basically, this is installing the new nodes. But here, what you need to do is basically take this node and break it into two nodes. Right? So the node n prime and also node O here. And then remember that this is a copy on rate tree for the internal node parts. Right? So what we do here is actually copy this parent node as well, and then put the new key, the new separated key, as a result of the separation of these two nodes. In here, and also the new pointer pointing to the new node, both nodes actually. And then also we need to change the pointer that's in the grandparent that's pointing to this guy here, right? Because we're creating a new parent node, so that means the pointer in this guy needs to be changed to point to the new one. Yes.
I presume you're logging all this so you can crash and have crashing.
Yeah. Yeah, no, well, those are actually covered in PMwCAS. So PMwCAS internally does everything for that. Yes.
And readers can progress while this is happening?
Yes, so readers, that's more about PMwCAS actually. So what PMwCAS does is it will try to first sort of lock the word by swapping in the pointer to the descriptor on that word. So when another thread sees, this word actually contains a pointer to a descriptor, you will actually dereference that pointer and go in to finish the PMwCAS for it. So it's actually kind of a help along cooperative process.
But if there's two people trying to split this node at once, one of them gets the frozen state.
Yes.
What happens to the other guy?
The other guy, there's different policies you could do here. You could just say, I will also do this one, try to race with the other guy. Or I could wait, just retry. So it's...
But waiting, I mean, this is supposed to be lock-free. If you're really
exactly.
Waiting, you're kind of
yeah.
made it locked out of
exactly. Yes. Yes.
Okay.
So I would say it's better to actually just do it, right? So you race with the other guy. Yeah.
Okay.
So there's a lot of such details in this one actually. We have code later, so you can. Okay. The idea is that we sort of do this in a three-word PMwCAS operation. So first of all, again, you need to freeze this node here, basically saying I'm kind of replacing this guy. You can say, for example, replace a pointer in here, right? And then also we need another PMwCAS entry there saying we are replacing a pointer in this node, which previously was here, then now we want it here, right? So and also it's actually similar to this one, which ensures the grandparent's status didn't change, right? So no more other concurrent updates to that node. So this is really sounds simple, right? It's relatively straightforward. At least when you read the paper, you will say, okay, this is a nice and clean approach, right? It's clear, like two-phase here. You stop new inserts and then you do the split, right? But so the thing is, first we have two problems to talk about here. One is sort of simple and easy. Basically, this is a persistent memory leak. First of all, you will notice here that we have new nodes allocated, right? But these new nodes, they're not really owned by the tree until the PMwCAS actually succeeds, right? So in other words, you need something else to own it. And also the old node here, we need to free them, to return it back to the allocator. But this is only if the PMwCAS succeeds again, right? So PMwCAS actually got it covered. It supports this sort of interaction between the data structure and the allocator question.
I'm sorry, the change from the before state to the after state
Yes.
is the pointer swing of the pointer from G to P to G to P prime?
Right.
So isn't that a single word comparatively?
It is, but you do also need to change the others altogether. Like there are three things here happening. Yeah, it's not just the pointer change. It's also making sure your status didn't change. Yeah. So that makes a multi-word. Okay. So we have this facility called actually memory policy for each of these words here. So essentially in the descriptor, this part is what we already talked about, right? And we have this new part which is specifying the memory policy here. So for instance, if we're looking at the first grandparent node, we're trying to change it from pointing to this P node to this P prime node, right? So what we really want to happen is actually when the PMwCAS succeeds, we want the old value to get recycled, freed, returned back to the allocator. But if this PMwCAS actually failed, then we want the new node to be freed, returned to the allocator, right? So this is what this free one policy here is for. And then there's also other kinds of policies, like for example, I don't really care, and then I only care if I crash, then on recovery I can return all the memory back to the allocator. So there's also such a policy. Right? So so we will specify the policy for each of these words. Right? Okay, so now this is what it actually looks like. Apparently this one has a bug. It actually doesn't work, and that was one of the initial implementations. So this is for splitting, right? We're getting the descriptor here, and that's my student. This reserve and add entry call is something that we designed to specifically cope with this scenario, where you first, if we come back to this one, essentially what it says is first I reserve one of these entries, give it to the application. And then the application can take the actual pointer to that field and give this field to the allocator, saying you can put the address of the new allocated memory here, right? So it's like basically POSIX memo line. And then we can safely, kind of the PMwCAS now at this point will own this piece of memory, right? And then now if you hit a crash, the recovery mechanism in PMwCAS will be able to return all this memory to the allocator, right? So essentially it's owned by PMwCAS before you actually hand it over to the application. Yes?
So this is a motif that shows up in lots of these libraries where something gnarly has to happen on memory allocation.
Yeah.
And it just occurred to me, like, do we need to somehow rethink the notion of how allocators work, and like is PMalloc like fundamentally the wrong way to think about this, because somehow you have to have an atomic assignment to keep from losing data, blah, blah, blah.
Right. Yep.
And then there was something, I forget what it was, someone was talking about fragmentation earlier.
Yes.
And it seems like there's the allocator, as we've imagined, is broken. Right?
Yeah, this whole thing is just needs to be kind of rethought of, and then you need to have a kind of systematic way of doing all these things all together. And this one is focused more on the interactions between the library and the application, the programming library, and the allocator. So these three things, they need to be considered all together to kind of have a usable data structure here. Yeah. Well, I don't have an answer, so that's my thought so far. And another caveat here is actually, so here this call get new value pointer. That's giving you the pointer to the field that's in the descriptor, right? And that's the thing you're going to feed into the allocator. And here we have 0, 1, 2, right? So this actually maps to 0, this guy, 1, this guy, 2, and this guy. So in other words, you can't really change the order of these things. You have to remember, like I first got one entry here. It's maybe for my right node, and another entry for my left node maybe, and then another entry for something else.
They'll become visible in that order.
Yes,
Right.
yes,
That's
because
the
that's the order that's exposed to the application. Yeah, so that's a tricky bit. Okay, this kind of we kind of have it working, right? So although the allocator we probably need such an allocator, actually we made it work with the PMDK allocator using the transaction stuff there. Oh, okay, good. So, all right. So, but the real problem here is actually tree growth. It's if you think about this whole process, this is actually easy if you only have to like replace the pointer in kind of one level, right? But so I see viewers laughing here because B-trees they grow, right? So the split can actually propagate up and grow the tree. This means your descriptor size in the end would actually scale with your data size, meaning you could have a arbitrarily long descriptor that contains all the nodes you have to ever touch along the entire path, and when you grow the tree, right? So essentially, this means it's probably bounded by the current number of levels of tree plus 3, I guess, right? So 1 for the left, 1 for the right, and also 1 for growing the tree with a new root node. So in the end, remember that in the beginning I talked, I said the descriptor size is actually fixed because it's 4, and we didn't really anticipate that people would use it this way. Most of the cases, if you look at the paper as well, indeed they actually say, oh, this operation only requires 3-word multi-word compare swap, which is kind of not really the case, right? But you could actually do it because one alternative is to kind of split and propagate one level up at a time, right? So you only do this one at a time, and then when you temporarily allow the kind of the parent level to be oversized, and then split it again, up until you propagate to the top level, right? So, but our current implementation basically goes like we are limiting the size of the tree, essentially the height of the tree, maximum height, and then pre-allocate space in the descriptor. In other words, even if you're doing a single word PMwCAS, you actually have to allocate an allocator that's descriptor that's capable of containing, say, 8 words, right? Which is kind of waste of space. And also, you have to modify PMwCAS descriptor size. And just in order to do this, we actually introduced a macro in the code so that at compile time you can customize it. Another alternative, I don't think I have it here, which is you can make the descriptor variable size, right? So you can specify how many fields I want and so on. So, but in that sense, your descriptor management code now becomes itself an allocator, right? So there's a trade-off over there. So how much do I have? 5 minutes?
You have about 5 minutes.
Okay. Let me try to show the actual code. It's too long to be pasted here, so. All right. Yeah, that's the double linked list code, and I think BzTree is here. So, okay. So this one is the main kind of entrance function for you to actually split the node. Okay, so the beginning part, these ones are straightforward. You just get the new node and so on. What's actually happening is, let me see. It's actually
There's your busy wait right there that we were talking about, right?
Yeah, exactly.
So somebody else froze it.
Yeah, there you go. And also there's also a backoff parameter that you could tune. And here then, this is when you find out, oh, actually the parent also needs to kind of split, and then you propagate it up. So the parent node here, this one, although it has the same name, it's the C++ inheritance. So it's the same base node with the same function name, but different implementation. So let me see. internal node prepare for split. Yes. So that's how it looks like when you split the internal node. And so basically here we're trying to reserve the entry. The address here is no address because we don't know yet. So we don't know which word to change yet. And then here you're basically saying I want just an entry there. And this pointer L, that's the left. Pointer R, that's the right. And then you do all the necessary stuff by comparing the keys and put it in the left or in the right. And then, so here it's determining where to go. And then finally, in the end, there's I think, recursive call, which is doing this again, right? And you probably get one level up at a time. So in this whole process here, if you look at the parameter list, basically you have to give all these pointers first, so that in the next level, the allocator will be able to write the address onto this address, so that the PMwCAS can own this address, the memory block. Yes. Okay. All right. So I guess it's not so simple, right? So and the paper kind of presented a way saying it's kind of simple, right? But I kind of feel it's not really there. Okay. So now, what's beyond this? So if you think about it, whether it's easy or hard, it's really not about concurrency anymore at this point. It's more about the consideration about the interactions with PM library and the data structure, right? So it actually impacts how you design the data structure. And like I said, it's the three pieces here, right? So allocator, the programming library, and also your data structure design. So for something after BzTree, which I don't know, I'm not a native speaker, so I don't know there's another thing here. If you know, let me know. So basically, if you were here again, so Lucas' talk actually covered a lot of it already. One thing here we want to have is actually we don't want to use copy on write. It really puts too much pressure on the allocator, which is not really a good thing. And this also shifts the responsibility of having, basically you are relying on the allocator to perform, to be high performance, to be able to get good performance, which is, again, that's a varying factor we don't want to really depend on, right? And also interactions with persistent memory allocator, like we already discussed. So we had a bunch of implementations. It's available here for the tree. So we tried to talk to Microsoft, but they said it's kind of unlikely to get it open sourced. So we had to build our own, but it is what it is. Then PMDK now, PMwCAS now with PMDK support is also open source. But this one we did get it into the official repo of that's maintained by Microsoft. So again, pull request and bug report, welcome. So that's it for me.
So, time for a final question or two?
Yes.
Yeah.
So, this is still kind of hard.
Yes.
So, how easy can we make it? Like, you stand where you are and you look towards the land of the ponies. Like, how good can it be? How easy can it be to take something like this, or its successor, or its successor's successor, and quickly build an interesting data structure?
Well, I find, so my own experience is the kind of quicker you get, the data structure becomes more standard and generic, and then you probably don't really have the high performance, at least at this point. So to be honest, I don't really have a solution here. And in terms of how easy can this be, I think we pretty much got the concurrency problems covered. So now at least you don't need to reason about the data resets that's happening to a large degree. Right? So you still have to think through what are the interactions with multiple threads, but it's much easier than just purely using the single word compare and swap. So I think we're getting there, but these are the things we need to figure out next, I think, to be able to tell whether how easy it could be or whether it could be easier at all.
Based on the time, I really need to keep things moving because I don't want our third speaker to be hampered by the lunch break. But thank you very much.
Yeah.
Appreciate that.